So how do missiles intercept moving targets? To explain how missiles intercept targets, I will be using car as an analogy, because car behave in a similar way as a missile. It has its front wheels and it steers with it. It moves and steers. Similar way, the missile also steers with canards. It has an extra pair of canards for the up and down movement. Although, depending on the orientation of missile, up and down is kind of a relative. So here's the dynamics, sort of now approximate the dynamics of a missile. You can see that it sort of behaves like a car. However, it slips. It's like this car but moving on ice. But general principle stays the same. Which is why for the remaining explanation in this video, I'll be using cars instead of missiles. Because then the explanation is a bit closer to a real life, I guess. Now let's try first a simple approach. You can see this car simply turns its steering wheel towards me. It will try to look in my direction. And if I let this car run forward, it can easily run me over. Here's the car. It will turn towards me. And run me over. However, I can easily avoid an interception by simply not being stationary. You can see. So this method isn't gonna work in case for missile, because usually the target for the missiles it moves, it tries to evade. And what's also so special about this method is that it's not gonna try to intercept me really. It's just gonna rather follow me. You can see. Now this property of this control method is why this method is called a pure pursuit algorithm, because the missile will simply pursue the target. It's not gonna actually attempt to go right in front of me or anything like that. Now those two cars, they are set up in such way that they will collide with each other. Look at them. But now let's try to look it from one of the cars' perspective. Now it's the same situation, but we look from this car's perspective. You have the camera, it is pointed right at this car. You notice how the line of sight didn't change towards us. The car was simply starting to grow bigger, but it wasn't really moving from the perspective of this first car. Now I will show you the same scene but I will also draw this line of sight vector. And look how all those lines are parallel to each other. But here's the different situation. The car will be moving a bit slower than previously. And look at the perspective from it. This line of sight vector from this car towards this one, it appears to be moving to the left. And this is how the situation will look with line of sight vectors. You can see that those lines turn slightly to the left. And if this car looks faster than it needs to be, and that's how it looks with these lines. You can see that this line of sight appears to be turning to the right. Now this property with line of sight not turning, not changing, is the most important one. If it's not, the line of sight is not changing, that means that the objects gonna collide with each other. So I implemented this control system in the car. When I turn to the right, when I move to the right, you can see it turns its wheels to the right, to the left, from the car's perspective. But it's not actually turning the wheels towards me. It's only reacting to the change of line of sight. And this, unironically, is gonna be way more efficient in intercepting me. Let me show it to you. As you can see, it can intercept me if I'm standing still, but it is also really effective even if I'm moving. So let me show it to you from the car's perspective. It's gonna get stuck soon. Okay, I will help the car a little bit. Now the method that I show you, with which this car was able to easily intercept me, is actually called a proportional navigation. And here's the formula. It's a theta dot equals phi dot by n. And phi dot is the speed of rotation of line of sight. So you can see this target. And here, if I keep rotating it to the left, it is rotating left with certain speed. And if I keep rotating to the right, it is rotating right with a certain speed. And what this formula tells us is that theta dot is a speed of rotation of a car. And to simply show or what will be the effect, I will explain the effect of the n. I will set the n to 1. Here n is set to 1. You'll see that the car rotates right with the same speed the target is rotating. But the thing is, the car isn't actually trying to point in the direction of the target. You can see it. It simply maintains relative rotation speed. Now, our system, the proportional navigation, actually meant to be run with n equals 3, where after only one rotation of our target, so if it rotates, say, 90 degree, our um, our car will rotate 270 degrees. This value can be set to 3, to 4, to 5, or anything in between, but it should be set at least to be 3. If you set it to 2, it would, I believe, also work, but it will have certain problems. And that's entire thing. The reason why it's called proportional navigation is because the rotation of our car, our vehicle, of our missile is proportional to the rate of change of line of sight. That's all. Now let me show you the effects of different values of n. When n equals 1, the vehicle will be rotating with the same speed as the speed of change of line of sight. So if I stand right in front of the vehicle and then I start it will be able to actually kill me, because it essentially behaves like a pure pursuit algorithm. But if I'm not right in front of it, then the system will just miss completely. If I standing like right to 90 degrees in front of it, it might just start circling around me, because it will be essentially rotating with the same speed than the line of sight from me to the vehicle. Now, when you set the n to 2, then the system sort of gets the ability to intercept targets, but you'll see an issue with that. Look at the steering. Look how the steering actually starts to increase. It will be able to intercept its targets, but it's not going to be an efficient one. And you know, this steering on the missile, it creates resistance, so the missile would be losing a lot of energy, and uh, consequently range would be reduced. But if we set n to something like 4, you can see how much different it will be. I will be again moving, and look, the steering actually decreases. And the reason why that happens is that it's because the car starts to point. It's essentially, it actually finds this perfect interception point, and you know, imagine I'm moving here and the car will be moving here, and that's an interception point. At that point, the line of sight is gonna stop changing, and basically the missile or the car, it simply glides towards the target without wasting any energy. It just moves straight. Look, steering starts to decrease because car simply moves forward. I hope I managed to show you what's the point of this uh, proportional navigation. Let me show you a last example. Now it found the perfect interception point, and the steering becomes 0%. Well, almost. There is small mistakes, small errors in the control. It's because of how this thing doesn't perfectly turn. That's all for today. Thank you guys, and goodbye.